Topic 1.3 shows up early in the course, but it produces some of the hardest questions on the AP exam. And here's the strange part. Every year, students who fully understand this topic still get these questions wrong. The exam writers present them in a way that's built to trip you up. In the next few minutes, I'm going to break down this topic, show you how to spot these questions on the exam, and map out exactly how to solve them. By the end of this video, even if you hit a strange new variation this year, which is likely, you'll navigate it easily and pick up the points that most students leave on the table. This is the full list of material from topic 1.3. I'm going to work my way through each part listed here, and then I'll combine them together at the end of this video into a true AP-style question that will evaluate not only your understanding of the topic, but your ability to earn the points that I promised you. Percentage calculations are all over AP Chem. Instead of applying unique equations in each instance, my approach can be applied to every percentage problem throughout the course. To calculate a percentage, simply divide the system by the whole and multiply by 100. The system, as this term is used throughout AP Chem, is whatever your focus is. For example, a test grade from one of those math teachers, or possibly your chemistry teacher, that is given in the form of a fraction. The percentage you're calculating for this is your grade, or the points you earned out of the total possible. The numerator is the system, how many points you earned. The denominator is the whole, the total number of points on the test. It makes intuitive sense because you understand what you're calculating. If you understand the percentage you're calculating on the exam, you'll be able to do the same thing. Fair warning, the mistake most students make with percentages is not moving the decimal properly. Most of the time, you'll punch this into your calculator, then recognize that 0.96 is equal to 96%. When you apply this to grades, you're not actually thinking about moving the decimal 2 places, you're just turning it into a 2-digit number. Unless you earned 100, but then you're probably not plugging it into your calculator. Let's get into the chemistry, and I'll point this out when we get to it. The chemical formula for water is H2O. The formula indicates that there are 2 hydrogens for every oxygen within this compound. So if I have 1 molecule of water, then there are 2 hydrogen atoms and 1 oxygen atom. If I have 1 mole of water, then there are 2 moles of hydrogen atoms for every 1 mole of oxygen atoms. This 2-to-1 proportion for hydrogen to oxygen is always the same for water molecules according to the law of definite proportions. But the percent composition is based on the mass of hydrogen and oxygen within the water molecule, not the moles or the atoms. Which brings me to the main concept applied in 1.3. The formula gives you the ratio in moles, but most measurements are in grams. Well, what measurement converts between grams and moles? The molar mass. So the main concept is using the molar mass to convert back and forth between the formula and the mass of each component. Let's run a calculation so you can see how this is applied. I want to solve this from the perspective of my percentage equation. Even if you understand how to solve this problem, I'm also teaching you techniques that will be used throughout AP Chem. Writing down equations may seem like wasted time, but students who do so always perform better. Not only does the act of writing things down trigger your brain function, but seeing your work on paper helps you think through the process. I'm calculating the percent of hydrogen, so the system here is hydrogen, and there are 2 of those. This is the proper way to write 2 hydrogens. H2, as written in this formula, means that the 2 hydrogens are bonded. But if I want to list 2 hydrogens, I write 2H. And I know what you're thinking, but yes, symbols matter. Use them correctly. The whole thing is the water, and don't forget to multiply by 100. Now I have the setup, but I'm calculating the percent composition by mass. That means I have to plug the molar masses for each substance into this fraction. I'll need those. Normally, I like to perform my calculations all at once, but calculating the molar mass of water within the fraction is uncomfortable for me. I'm going to do that first, then plunk it into the denominator. Feel free to choose your own method of problem solving, but if you ever notice you're consistently making calculation errors, there might be a more efficient way to go about doing it. I'll plug that into the calculator and get 11.19%. These are reasonably straightforward, same system every time, so let's keep rolling. The next question deals with 2 different ways of writing chemical formula. This is where the concept comes in for solving the big free response questions that I'll do at the end. Take the time to understand the chemistry before you try fumbling through the problems. The molecular formula is the true chemical formula for a substance, while the empirical formula is the reduced form of that formula. Consider the chemical formula for ethane. The ratio of carbon to hydrogen is 2 to 6. which can be reduced to 1 to 3. So the empirical formula for ethane is CH3. There are also far more complicated compounds, like glucose, a common sugar molecule. 6, 12, and 6 in this case are all divisible by 6, and so the empirical formula for glucose is CH2O. Just reduce each one of these down. Think through a few of these and watch out for the traps. Like the first one, the 2 and the 6 do reduce, but there's only one oxygen. In this case, the empirical formula is the same as the molecular formula. C4H10, 4 over 10 reduces to 2 over 5, so C2H5. C3H8, 3 and 8 can't be reduced. The empirical formula is the same as the molecular. The last one, 6, 6, and 2 are all divisible by 2, so 3, 3, and 1. This makes for great multiple choice questions, but make sure all subscripts are divisible by the same number, otherwise the empirical formula is the same as the molecular. There's another common multiple choice question that's quick and easy that winds up being a time suck if you can't connect two concepts together. Each of these compounds has the same empirical formula. If the molar ratio is the same for each, then the ratio by mass is the same as well. Take a look at this AP-style multiple choice question. The exam writers love to write questions that appear like math problems, but turn out to be concept-based. Remember, this is a chemistry test, not a math test. By including the percentages, students always want to do something with those numbers, but that's the trap. C6H6 has an empirical formula of CH. Only choice C has the same empirical formula. Two compounds with the same empirical formula have the same percent composition, so C is the correct answer. AP level questions will provide you with tons of contextual information, but just because they're numbers doesn't mean the question requires calculations. Each of the 1.3 free response questions you'll see on the exam will go through several steps to ultimately find the same thing. And I built a simple system that will take you from start to finish on any question, no matter the starting point. I'm going to use this example to introduce the system for finding the empirical formula for a compound. Let me start by extracting the details from this word problem. There's an unknown sample. It's made of this percentage of iron and the rest is oxygen. Then I need to write the empirical formula. That's all I need. The rest is just words. The given information is always different, but the first step is to make sure you have the mass of each element. This will be the ratio by mass. The question said that the sample was only iron and oxygen, so together they add up to 100%. But I have percentages, not mass. There's a few ways to convert from percent to mass, but I like to just assume that the sample is 100 grams. In a 100 gram sample, that's 69.94% iron. I'll have 69.94 grams of iron and 30.06 grams of oxygen. That's step one. Next, I want to convert both of these into moles. Dimensional analysis was covered in topic 1.1. Feel free to check out my video on that one. It's a simple process, but quite possibly the single most important topic in all of AP Chem. I put the molar masses up, but always keep your periodic table handy. Questions may or may not provide you with molar masses, so you'll need to know when to break out your table. Start with the mass and fraction bar. I have grams, so that goes on the bottom. I want moles, so that goes on the top. And the molar mass is the grams in 1 mole, so 1 goes next to the mole, and the mass of each goes next to the G. Divide each of these and I'll get this. I just wrote 4 sig figs on each of these because my final numbers are going to be integers. 4 sig figs is plenty. And that's in moles of iron and oxygen. Notice how organized my work is and that every number is labeled. Organized students outperform the unorganized every time. Step 2 is done. I call this the ugly mole ratio because this is not an acceptable chemical formula. I still need to clean up this ratio before I can write the formula. To do that, I'll divide by the smallest number in the set. This will reduce the smallest value to 1 and give me a clearer idea of how to write the formula. These are my numbers. 1.252 is the smaller, so divide each by that. And that will give me 1 mole of iron, and my calculator says 1.50079, which I'm going to write down as 1.5 moles of oxygen. It's pretty close. That does cover the last step in my process, but I can't use the 1.5 in the chemical formula. I also don't want to round the 1.5 to 2 either. The mole ratio is in fact 1 to 1.5. The problem with dividing by the least is it assumes that the smallest number in the formula will be a 1. That's not always the case. When your cleaned up mole ratio has a number that's something 0.5, just multiply everything by 2. This will maintain the ratio while converting everything to whole numbers. A 1 to 1.5 ratio is equal to a 2 to 3 ratio. I would highly recommend spending some time practicing these problems before moving on to the experimental questions at the end of this video. Those problems are going to add more steps and complexity to this process. The more comfortable you are with this 3-step process, the easier the later problems will be. That being said, there's also a quick version of this problem that doesn't require a calculator. And it makes for a perfect multiple choice question. Let me show you a possible shortcut while reinforcing the process. I'm given the mass of each element in the sample, so let's just pull those numbers. That's step 1. I need the molar masses to convert to moles. Wait, the mass of magnesium and carbon in the sample are really close to their molar masses. That means I have 1 mole of each of those. What about the oxygen? If you don't see it, set up the dimensional analysis, and you'll recognize there's 3 moles of oxygen. This one gave me a clean ratio. I don't even need to do step 3. I can write the formula as MgCO3, my 1 to 1 to 3 ratio. Notice how this question tested your understanding of the process while minimizing the math? Be prepared for both types of questions throughout all of AP Chem. In either case, this 3-step process is valid. The last bit of new information involves determining the molecular formula from the empirical formula and the molar mass. The ratio for C2H6 is twice that of CH3. I consider the multiplier here to be 2. The molecular formula is double the empirical. The multiplier is also equal to the mass of the molecular formula, or the molar mass of the compound, divided by the mass of the empirical formula. The mass of the molecular formula is 30 over the mass of the empirical formula, 15, and that is equal to 2. The multiplier can then be used to convert the empirical to the molecular formula. As I said, CH3 times 2 gives me C2H6. But what does this look like in practice? Always start by extracting the necessary information. I need to write the formula for this thing, given the mass of each element, and the compound has a molar mass of this. All right, let's clear out the rest. I have the mass of each element, so I should find the empirical formula first using the 3-step process. Get the molar masses from the periodic table. And another easy one. The mass of each element is half the molar mass, so there's half a mole of each in the sample. If the sample contains half a mole of each, that's a 1 to 1 ratio, so the empirical formula is HO. This equation will calculate the multiplier. MM is the abbreviation for molar mass, and I'm using EM for empirical mass, or the mass of the empirical formula. The question provided the molar mass, and I'm going to estimate the empirical mass. The multiplier is always a whole number, so 17 is close enough. Now, plug in the molar mass and the empirical mass, and I get a multiplier of 2. If I double the empirical formula, I'll get H2O2, and that is the molecular formula. Remember that if the molecular formula has 3, 4, or 5 times the stuff in it, then the mass of that formula will be 3, 4, or 5 times as well. It just so happened that both my examples were double. It won't always be a multiplier of 2. That covers all the content for 1.3. What do these look like when they show up in the free response? One of these 3 experimentation types have shown up on the exam each of the past few years. Each one requires an empirical formula determination, but most students didn't realize that these are solved using the same process. They're not completely different questions. I can't promise you that one of these experimental techniques will appear in the exam this year. In fact, based on past experience, it's likely to be something totally different. However, fundamentally, these are all the same. Get comfortable enough with these, and hopefully you'll be prepared for whatever's thrown at you this year. If you haven't seen one yet, this is what a typical AP free response question looks like, although many of them have more parts than this. There's a lot to unpack here, but don't panic. Most of this is background information and not relevant to solving the problem. Just extract what's necessary and ignore the rest. All those words above the data table basically state that copper turns into an unknown CuCl compound. Now I can move forward. Extracting the right numbers from a data set will be assessed on the exam in multiple places. Drawing pictures will help significantly. The first line is just the mass of the beaker. The second is the copper in the beaker. The third line is the beaker with the copper and chlorine that reacted. Don't worry that they're technically bonded together. Any amount of these two elements that reacted were measured within the beaker after the experiment. The nice thing about the free response questions is that complex problems are broken into multiple steps, and that will help guide you. Part A is asking for the moles of chlorine. Use the pictures that you drew to help you figure out how to find it. The only picture with chlorine in it is the third one. However, this includes the beaker and the copper, which is represented by the second. Subtracting that will leave me with only the mass of chlorine. This question is asking for moles. Look up the molar mass and use that for the conversion. Like this one, most AP free response questions do ask for your answer in a specific unit. Without converting this to moles, you'll lose the points for this part, even if you get the next two parts correct. Part B is asking for the moles of copper. If I take the copper and beaker, the second number, and subtract the beaker, the first number, I'll have the grams of copper. Look up the molar mass and use that to convert from grams to moles. For part C, I'm going to need to write the empirical formula. The answers for A and B tell me that I have an ugly mole ratio. At the same time, these are really close, within experimental error, close enough that I can call this a 1-to-1 ratio and safely write the formula as CuCl. Fair warning, the data in the table can be presented in a variety of ways. Don't memorize the way I solved this problem. Instead, draw the pictures representing the data, and you should be able to extract the numbers you need to work the problem. Other than that, the rest of the process was the same as the basic empirical formula questions I did earlier. Find the mass of each element, convert to the ugly mole ratio, and clean it up to write the formula. Hydrate analysis involves hydrates, obviously, which requires a quick explanation. Hydrates are ionic salts with water molecules chemically bonded within the structure of the salt. The chemical formula for a hydrate lists the mole ratio of the salt to water. For example, the hydrate shown in the image here is calcium chloride dihydrate with a chemical formula of CaCl2 times 2H2O. According to the formula, for every 1 mole of CaCl2, there are 2 moles of water. That 2-to-1 is the mole ratio you'll have to solve for in hydrate problems. Nearly all hydrates also have 1 mole of the salt to more moles of water. So this is the number you'll be calculating in these hydrate problems. Here are some other common hydrate formulas so you can see what I mean. Now, for the actual question. When writing the empirical formula for the CuCl in the previous problem, the 2 components I needed to solve for were the copper and chlorine, the 2 elements. I'm still looking for a mole ratio in this question, but the ratio is the salt to water. That's CaCl2 to H2O. The question has 3 parts that walk me through the overall process. I'm going to start by drawing some pictures so I know what the numbers in the table represent. If you haven't done this experiment in class, a crucible is a small porcelain dish used to heat things. In this case, evaporate water from the hydrate. It's just a container. The first number is the empty container. The second is the container and the hydrate, which includes the salt and the water. I'm just putting an X in front of the H2O for now because I don't know what number goes there. And the third number is the sample once the water is removed, leaving just the CaCl2 in the crucible. This is also referred to as the anhydrous compound, meaning without water. Part A asks for the grams of water. The second number is the only one that actually includes the water. Then I'll need to take out the anhydrous salt and the crucible, which is the third number. Plugging those into my calculator, I'll get the mass of water. I don't need another conversion here because this part asked for the mass, not the moles. Part B asked for the moles of just CaCl2. If I take the dish and the salt, the third number, and subtract the dish, the first number, I'll have the grams of the anhydrous salt. Plugging those in, I get the mass. B is asking for the moles, so I do need to convert here. The molar mass is still on the top of the page, so a little dimensional analysis, and I have the moles of the anhydrous salt. Part C. The formula is the mole ratio of the components I just solved for. The water's still in grams, and now it's in moles. This is the ugly mole ratio. Dividing by the smaller of the two gives me 3.9989, which is close enough to 4. The formula of the hydrate is CaCl2 times 4H2O. Still the same process. Determine the mass of the components, convert to the ugly mole ratio, then divide by the least to clean it up. The main difference is understanding what the components are. Of course, there's still one more variation. Combustion analysis involves lighting things on fire and measuring what comes out. Fun. This is a generic form for the combustion equation. The reaction burns hydrocarbons in oxygen and produces CO2 and H2O. By measuring the amount of carbon dioxide and water produced, it is possible to determine the empirical formula of the hydrocarbon. As with the previous two examples, this is the determination of a mole ratio. We had the two elements in the first one, the salt and the water in the second, and this time it's going to be the mole ratio between carbon, hydrogen, and for this one, oxygen. Hydrocarbons don't have to contain oxygen, that may be left out. The same system can be used to solve this one. The carbon from the reactant is converted into CO2, so that's the starting point. If I take the mass of CO2 produced, I can convert that to the moles of CO2 using the molar mass provided. And since 1 mole of CO2 contains 1 mole of carbon, I can write this. Plugging that into my calculator gives me the moles of carbon. For part B, the reaction converts the hydrogen to water. If I start with the H2O by taking the mass of water, convert that into the moles, then there are 2 moles of hydrogen for every mole of water. This is the spot where most mistakes are made. The formula for CO2 and H2O indicate the mole ratios that are taken into account in this step in the conversion. And it's written into the formula. There's 1 C in CO2 and 2 H's in H2O. Plugging that in gives me moles of hydrogen. Let me make some more space. The last part is asking for the empirical formula and simplifies finding the moles of oxygen. This is similar to the way combustion analysis was presented on the AP exam in the past. Determining the oxygen without this hint is possible, but involves a mathematical calculation that doesn't prove further knowledge of chemistry. If you're ever working problems or watching videos that result in long, repetitive mathematical calculations, stop wasting your time. You're studying for a chemistry test, not a math test. If carbon and oxygen are in a 1-to-1 mole ratio, then I know the relative moles of oxygen. They're the same as carbon, which gives me the ugly mole ratio for the compound. To clean this up, we divide by the least in the set, which gives me a nice, clean 1-to-2-to-1 ratio. The order of the elements in the compound formula was given in the problem up top, and I'm not sure if you'd lose credit for writing them out of order, but if you ever stop to wonder about something like that, look up. It was probably provided somewhere in the problem. The final answer is C, H2O. Each of these has appeared on the AP exam over the past few years. That means those creative people, that's the word I want to use, will put something completely different on the exam this year. To prepare for that, don't memorize these. Understand how each one works and the connections between them. Stick with me for another 30 seconds and I'll run you through those connections. Each question will likely provide you with experimental data and ask you to write the empirical formula for the compound. The data is typically measured in grams. Then, to write the empirical formula, you need the mole ratio of the components. Make sure you learn how to apply these 3 main steps to a variety of different compound types: data extraction, converting to the ugly mole ratio, then dividing by the least to clean it up. These are the 3 I've seen on the exam over the past few years. If you're skipping around in the video, I walk through examples of each, and I'm not here to waste your time, so go back and watch. The unknown salt and hydrate required you to extract the mass of the components from the data tables. They were a little tougher to start with, but if you draw some pictures, or at least picture them in your head, you should be able to extract the numbers that you need. Combustion's the nice one here and gives you the mass directly, but all 3 start you off with the grams of the individual components. Then you convert to the ugly mole ratio. This is where combustion requires that extra step. If you don't show your work and that you've converted from moles of CO2 to carbon and moles of H2O to hydrogen, you won't get credit. Make sure you understand this step and to show it in your work. Incorrect work on the AP exam means you won't get credit, even if you have the right answer. For all 3, dividing by the least will clean up the mole ratio. Then, write the formula. The main difference between the 3 question types is the components you're finding. The unknown salt and combustion analyze the mole ratio of the elements, while the hydrate was the mole ratio of the salt to water. If some strange-looking variation of this question shows up this year, just find the mass of the components, convert to the ugly mole ratio, then divide by the least. It may take some thinking, but if you practice at least these 3 variations, you should be able to recognize and solve the new one they're likely to throw at you this year. I think that's enough for 1.3. Remember that AP Chem is going to test your understanding of concepts and your ability to apply them. Memorizing specific problems or processes won't earn you a 5. Work the practice and look for the connections. Then you won't freeze up when things look different on exam day. If you made it this far, thank you. I created this channel because there's nothing better than watching a student go from confused to confident. So if this helped, please hit subscribe. I'm building out over 100 videos to cover every topic in AP Chem this year, and every subscriber tells me it's worth finishing. And remember, don't just memorize it, understand it. Be well.